Well, it's a great pleasure to have Xiao as our speaker. And I want to express special thanks for staying up very late. I don't know, it's pretty late in the evening where it is. So it's kind of unusual. We often have talks, but Xiao has done beautiful experiments with spin qubits, and there were several exciting papers all published back to back. And he's here to tell us about what advancements have been made. All right, go for it now.
Okay, you can. I think you can see my screen sharing. Or can you see?
Yes, we see your screen, and we have you pretty loud.
Yeah, and you can see the screen, right?
Yeah, we see the screen.
Okay. All right. So thanks, Yuna, for the introduction, and thanks for the kind invitation. So yeah, it's really my pleasure to come here to give this talk. And in this talk, I will present our recent work on high fidelity gates in semiconductor spin qubits, and especially a high fidelity two-qubit gate. And considering the background of the audience, I would like to spend quite some time to introduce some basic knowledge about spin qubits. And okay, yeah, here comes the outline. I will start with the background, which might take some time. And then I will go to the first experiment, which is the two-qubit character randomized benchmarking. And then I will go to the most recent experiment, that is high fidelity two-qubit gate verified by GST. Finally, I will do a very quick summary. So for the background, yeah, when we are talking about quantum computer, I think there are two candidates that are mentioned most often, and they are superconducting qubits, or let's say transmon qubits, and trapped ion qubits. But actually, in recent years, semiconductor qubits joined the game as well, and it starts to get more and more attention. And there are several advantages, or let's say potential advantages for semiconductor qubits. And the first one is that it's positioned very well for scaling, for upscaling, and yeah, because they are in semiconductor, and we can leverage a lot of industrial fabrication. And also, I mean, these qubits are really small. They can be made in the transistor level. So in principle, we can make very high density qubit array. And spins, normally we make spin qubits instead of charge qubits in semiconductor. So for spin qubits, they typically have pretty good coherence time, because theoretically, yeah, I emphasize theoretically, spin degree of freedom does not couple to charge or electric field, which means it is supposed to be very robust against the charge noise and the electric noise. And moreover, we have also shown that these qubits can work at elevated temperature, like 1 to 4 Kelvin. So in principle, so we call it hot qubits. And in principle, we can also bring down the control electronics to cryo, and then they can be easily integrated in future. And yeah, this brings solves the wiring problem and latency in the feedback, etc. So there are two major approaches in spin qubit. The first one I want to quickly flash is the one proposed by Bruce Ken in 1998 in this very impressive single-authored Nature paper. So in which, yeah, let me find my cursor. Yeah, can you see my cursor? Sorry, quick question.
It was there, but it disappeared. Oh, now there. Okay. We see the cursor now.
All right. So apparently, all right. So I think I need to play some trick. All right. Okay. Now it's easier. Yeah. So in this proposal made by Bruce Ken, one can implant phosphorus donors into silicon. So you can use the nuclear spin in the phosphorus donors as the memory qubit, because nuclear spin, we know that they are very well localized, very strongly confined, and they don't couple to, basically they don't couple to anything. You can imagine it's basically trapped ion, but trapped in solid state. So you can use that one as memory qubit, and you can use the spins of the electrons bonded to the nuclei as the computational qubits. and electron spins, they are easier because they are charges, so they are easier to manipulate.
Xiao, we are seeing the presenter view. Maybe you want to switch.
I see. Just now I made a mistake. Sorry.
It's okay. Good. Okay. Very good. Yep.
If you want, you can right click, and then there's a place where you can choose your pointer to be like a virtual laser pointer thing.
Okay. Yeah.
Pointer options below that, then laser pointer.
Yeah. Cool. Okay. Yeah, because I actually wanted to see the cursor in the presenter view, so that's why I swapped them just now. But yeah. I screwed it up, but okay, now it works. Yeah, so that's where was I? Yeah, I was finishing the introduction of the Bruce Kane proposal, and in Delft, actually, we are working on a different approach. That is the this one that's proposed by Daniel and David DiVincenzo in the same year in 1998. Maybe, yeah, depending on whom you ask, someone may tell you it's in 1997. Yeah, in this work, basically, one can fabricate a lot of gate-defined quantum dots. A lot of metal gates on the surface, on the top surface of the substrate, the silicon or whatever semiconductor substrate, and put some voltages on all of the gates to locally electrically confine electrons in the material. Yeah, so we actually define our quantum dots in the heterostructure shown here for all the recent work. I mean, in the past, we do it in gallium arsenide, and now we all do it in silicon. So it's a silicon heterostructure, which is the silicon quantum well, typically about only a few nanometer. In this particular case, it's 8 nanometer, but more recently, we switched to 4 nanometer or 6 nanometer for some complicated reason. And yeah, it's 8 nanometer silicon quantum well, and yeah, very importantly, we want to purify the silicon. So it's mostly silicon 28, and it's sandwiched by silicon germanium buffer layers on top and at the bottom. At the very top of the substrate, we fabricate all the metal gates, and you can see this pattern here. Basically, yeah, they are all metal gates, and we can put some voltages positively or negatively on all the gates, and then we can locally confine or trap electrons underneath the tips of the LP and RP gate. P typically means plunger, so yeah, we call them plunger gates. And this B gate, that's a barrier gate, which controls the height of the wall between the two quantum dots. So basically, you can use the B gate to vary the height of the barrier between them. And the MW gate is MW refers to microwave. So we apply microwave signal here to perform the single qubit rotations. So if you sweep the voltage, or if you change the voltages on LP and RP gate, for example, here you change them from let's see, in this range at LP on the y-axis, you can obtain such a figure, such a diagram, which we call charge stability diagram, and you see a lot of lines here. They are basically, you can understand it easily as phase transitions. Basically, that means the number of electrons indicated by the numbers in the bracket here. Yeah, we can change the number of electrons in the double dots. In most of the experiments, we want to precisely set the quantum dot or the double or the multi dot or into 1-1 regime, into the single electron regime. So here for the double dot case, it's a 1-1 regime here. So we have 1 electron precisely in each quantum dot. Because if you have 2 electrons actually they pair up, then you are not able to manipulate the spin states anymore. So the 2-qubit gate here, I would like to jump a little bit directly to the 2-qubit gates and later on come back to single-qubit gates. So for 2-qubit gate, we operated it using direct exchange interaction between the 2 spin qubits. So typically when we operate the 2 qubits, when we operate the single-qubit gates, like I said, there is a wall between them, which is very high. So so the qubits, they don't talk to each other. They are just separate spin qubits. So when you want to perform a 2-qubit gate, you want to turn on the exchange interaction, and there are 2 ways to turn it on. Conventionally, you can do it by detuning the chemical potentials between the 2 quantum dots, and based in the charge stability diagram, you can understand it as pulsing on the RP and LP gate along this axis towards the 2-0 charge configuration. 2-0 means 2 electrons in the left dot and 0 electron in the right dot. So if you pulse towards this direction, but not quite across not quite crossing this line, actually at some point, the electron in the left dot, or let's say the right one, it kind of tends to turn out to the left one, but not really there yet. But its wave function already starts to go into the other one, and their wave function starts overlapping, so the exchange interaction is turned on. There's another way which cannot really be seen in the charge stability diagram, because here you can only see the effect of the LP and RP voltages, but you can also directly control the barrier gate, which is a B gate here. If you make the barrier gate more positive, you are pulling the wall down, and once the wall is gone, basically the wave functions of the 2 electrons, they spread it towards each other, and they start talking to each other. So this approach we refer to as symmetry control, or let's say a 2-qubit gate at symmetry point. And later on, I will show you the difference between them. As for single qubit gate here.
Sorry, a quick question. Do you mind going back to the previous slides? Yeah, just probably simple. So how do we usually determine where 0, 0 is, or this 1, 0 thing is really just relative to some constant?
Yeah, it's a very good question. So so here I show you the charge stability diagram in the particular voltage window, but actually it doesn't mean that we can only take this diagram in this voltage window. We can take it like a ±2 volt. So basically, you can just go very negative, and at some point you will see no transition line, and that's a 0, 0.
All right, I see. Thank you.
So it's indeed the 1, 1 regime refers to absolute 1, 1 regime.
Okay.
Okay, so for single qubit gate, we choose to do the so-called electric dipole spin resonance. So I would like to take one step back. If you want to manipulate a spin degree of freedom, theoretically, spin does not directly couple to electric field, so you are not able to apply an electric field to operate the spin state. What you can do is to apply an oscillating magnetic field. And what we do in this case, for example, in this figure is taken from the paper by Manu Veldhuis in 2014. You have the spin qubit here. The quantum dot nanostructure is a little bit different, but never mind about that. You just need to know that the spin is somehow defined here. And you have a microwave antenna next to it, fabricated on the same shape. So once you send the oscillating current through the antenna, it produces, or it radiates oscillating magnetic field. And the spin is just next to the antenna, so it senses the oscillating magnetic field, and therefore we can perform ESR, meaning electron spin resonance. This is really a conventional method, has been used in many other fields as well. But we know that, if you apply a microwave, you use the magnetic field component in the microwave, it's really energetic inefficient. So ideally, we want to use the electric field component to drive the spin qubit. So which ideally allows us to drive it really fast. So the trick we play is to fabricate this thing you see on the surface. That's a cobalt, a micromagnet made by cobalt, which is a ferromagnetic material. So once you magnetize it, then basically it produces some additional magnetic field. So the real trick is here that once you magnetize the cobalt magnet, so let's see, now you see the BEXT, that's an external magnetic field we apply along this dimension, and it magnetizes the micromagnet. The micromagnet is made in a very special shape, so it provides magnetic field gradients. There is one gradient indicated by the green arrows here. You can see the small green arrows. Not sure if you can see it clearly, but these green arrows, they are pointing perpendicularly with respect to the external magnetic field. So now if I apply a microwave driving, let's see this one, so the microwave electric field quickly oscillates the wave function of the electron in the sample, in the material. So it oscillates in this magnetic field gradient indicated by the green arrows. So effectively, it sees an oscillating magnetic field, and that oscillating magnetic field can rotate the spin. And in addition, because of this small bridge on the right side connecting the two, these two squares. It provides a additional magnetic field gradient indicated by the green arrow, the light blue arrows, which point along with the external magnetic field, but with different amplitude in different quantum dots. So basically, this one allows you to have different Zeeman energies or different Zeeman splittings of the two spin states, and that gives you different qubit frequencies or guarantees the addressability. So this EDSR really has been done since many years ago, and initially it was done using actually not micromagnet, but the intrinsic spin orbital interaction in gallium arsenide, and later on, since 2008, this micromagnet design start to show up. So so far, I show you how quantum dot devices can be made in a university, or let's say in academia. But actually, these quantum dot devices can also be made in industry. So here I show you a schematic of the, let's say it's a cartoon image basically of the FinFET transistor based quantum dots. So very recently, my colleagues at TU Delft and at Intel collaborate, and they make this very nice work recently published in Nature Electronics. And you can see here, they really leverage the Intel fabrication. It's fully done by photolithography. There's no E-beam here, and they made this FinFET gate structure, and quantum dots can be locally defined underneath all the things. And they have shown actually quite decent coherence times and the gate fidelities that match very well with the state of art in academia. And you make it in industry, which means you do it using photolithography, so which means you can do it at a 300 millimeter wafer. That is really good for scaling, for producing many qubits and for the quality control.
Sorry, what back in that slide, I was trying to figure out what are those objects that you have labeled dumbification?
Sorry, I don't. Just now, it was a little bit lagging on my side. I didn't get the question very well.
The question was regarding this intriguing micrograph of the configuration. I see under where you have the cursor, it says charge sensors, and then right there, there's something called dumbification. What is that?
Dumbification, I'm afraid, is something regarding to some Intel standard fabrication process that I'm afraid that there's not too much to say about that. But about charge sensor, I can tell you a little bit more. So charge sensor is basically a sensor to detect the charge state. Let's see. Let me just quickly quit the full screen mode and sorry, because I have a slide hidden here, and I think it will be great if I show that to you. So for example, in this device here, I think you can see it here now. That's a device I'm using in the experiment I'm going to show you later on. So there is something called SQD, that means sensing quantum dot. That's a charge sensor. So basically, there is a current flowing through this charge sensor, which is also a single electron transistor, basically. So we use it to read out the spin state in the quantum dots. And you have for example, if you have a spin up state, you can align, you have a Fermi reservoir out of the quantum dot. That's a 2D electron gas. You can align the Fermi energy of the two decks well in between the two spin states, such that the spin up can tunnel out to the reservoir and spin down cannot. In this case, you can convert your spin state into a charge state. So if you have spin up, then you can make so means you have one in you have a one state, then you can release the charge. If you have zero, you keep the charge in the quantum dot. So you can convert the spin to a charge degree of freedom, and then you use the charge sensor, which is next to the quantum dot, to capacitively sense the number of electrons in it. And once you know it's 0 electron, just now I had a one state, it tunnels out. If you have 1 electron, it's a spin down, it's a 0, it never tunnels out. So that's a charge sensor, that's how we use it.
Great, thank you.
Yeah. So I will just continue. I think this slide was supposed to be skipped. All right. So we always talk about solid state qubits, and we say that they are great for scaling. And there are two major solid state qubit platforms. One is the superconducting qubit. Yeah, let me bring back the laser pointer. Or where is it again? Pointer options. Yeah. So yeah, there are two major platforms for solid state qubits. One is the superconducting qubits, another is the semiconducting qubits. And I guess if I just show you the SEM images of these two qubits, you probably won't tell the biggest difference between them until I put the scale bar here, and you can really tell now how small are the spin qubits and how big are the superconducting qubits. And even if I just highlight the Josephson junction area or the squid loop area, theoretically we can easily fit in millions of spin qubits. So that really make the spin qubits very easy for scaling and for you to make many qubits on the same chip. So actually, I'm not really intended to bash on superconducting qubits because they are doing great. They are doing really great job. But still, the footprint, the form factor of the superconducting qubits is really the elephant in the room. And you see that our colleagues working on superconducting qubits, they are really smart. They start making this chip-to-chip entanglement to solve the problem already from now. This is from the DiCarlo lab in Delft. And also, it's last year or 2 years ago from the Waraf group. It's a fridge-to-fridge entanglement, which is really awesome experiment, but also freaked me out. And more recently, this very cool work from the group of Andrew Cleland at Chicago, they achieve a GZ state transfer from one chip to the other chip with a fidelity of 65%. And just to go a little bit further, so here you see the most supreme quantum computer in the world, and you can find all the qubits here. Actually, you don't really see the qubits because they are buried in the math or the control lines. And on the right side, in the right, these are the control and readout electronics. And yeah, I'm not sure if anyone do me a favor and count how many cables are there here. And when you have more qubits, the number of cables you have might grow even faster than the number of qubits. But not if you do it in silicon. So if you're doing it in silicon, the chips, these instruments, they are just essentially the most important part in the instruments. They are just the silicon chips on the printed circuit board, and our qubits are also made in silicon. So in principle, you can just really make them all together on the same chip. And for long-term plan, this is really our vision, which was made in this very nice overview paper written by my supervisor, Lieven van der Sijpen. And you can see that we want to have a lot of local modules, and in each module there might be one or multiple logical qubits in each module, and between different modules they are connected by some kind of remote couplers, which might be photons in superconducting resonators, or we can directly shuttle electron from one side to the other. And also, I mean, it's in silicon, so we can just put all the control electronics on the same chip, and this can really reduce the latency and can solve the multiplexing issue. So for the qubit arrays, we have seen some very exciting work in the past 1 or 2 years. In this work is done, both works are done in Delft actually, and they are both the state of art. And this work is done in the Menno Veldhouse group, where they make qubits in silicon germanium heterostructure. It's not silicon quantum well, but it's germanium quantum well, and they have achieved a 3-qubit phase correction code in this device. And in the lower one, that's the most recent work made by my colleague Stefan Matouche, and it's from our group, from Lieven's group, and it's a silicon germanium 6-qubit linear array, and they have shown that they can entangle any 3 qubits, any nearest 3 qubits in it. And actually, I think so far there's no physical reason why we couldn't entangle all the 6 qubits, but there are some technical reasons. As for the spin remote coupling or the module coupling, the first way to do it is via the spin-photon coupling. So you can see the upper image that's from the PETA group at Princeton, and the lower one is from our group, from Lieven's group. So where we place quantum dots or qubits, 1 qubit at each side of the resonator, and we use the photon in the resonator to couple them to each other. And I want to highlight the most recent work by my colleague Patrick Harvey-Collard. This is a really nice work because he has shown that not only we are able to directly couple the spin qubits via a photon in the resonator, but for the first time we reach to spin-spin dispersive coupling, thus spin-spin directly coupling to each other with only virtual photon in the resonator. And the second approach I will quickly show you is the spin shuttling in the quantum dots that, like I said before, these are electrons. We can just transport them from one side to the other. And this work, very nice work from the PETA group at Princeton. They make the 9 quantum dots linear array in silicon. That they really show that they can shuttle a single charge from left to right, and they can shuttle 2 at the same time. Actually, yeah, 1 after the other, but operated at the same time, and 3 electrons sequentially. But one might argue, actually, this is not scalable because you have so many quantum dots, you have so many gates, and you have to firstly make this very complicated device to shuttle it from one side to the other, and how many control lines you will need here. Actually, this is not really the problem, and because now we are considering to work on this so-called conveyor mode shuttling. So you can imagine if I want to shuttle 1 electron from left to right, shuttle through all of these gates on the surface. I actually colored them in the period of 4. So basically the first, the 5th, and the 9th gate, they are all in blue, and I just connect them together, multiplex them together, and I multiplex all the red ones, all the green ones, and all the orange ones. So I only need 4 gates, and I only need 4, channels, input channels, and I can apply this sinusoidal curves to the 4 different gates, which produces a moving sinusoidal confinement potential, and this is the so-called conveyor mode. So you see, we actually need 4 gates, right? But actually, that's not right because we need only 1 gate. We can just multiplex them again and add phase shifters. So you need 1 gate to 1 channel, 1 control signal channel to shuttle the electron across between different remote modules. So yeah, here thanks for Inga Stadler and Lars Schreiber for allowing me to use this image from their unpublished work. Actually, they actually made this very nice conveyor mode. It's a SEM image, and you can really see that every 4 gates is connected to one control line, and finally these 4 control lines will again be multiplexed together. I'm very excited that this is really happening. So before I'm going to the real work, actually, the last one I want to tell you is about the control electronics. You
Could I
can see
ask
that
a question about that? Sorry.
Sure.
Excuse me. Thank you. I'm just a little confused. The picture is very impressive, and the gate scheme is very impressive, and I'm not meaning to. This is just really my naive confusion about what the state of the art is in the semiconductor versus the superconducting devices. As far as I know, right now, the only devices available on the cloud are still the superconducting devices, well, also IonQ, of course, from various sources. And I'm just wondering when we see a picture like this, what the state of the art is in terms of having realized these things in a quote unquote production mode with some non-trivial number of qubits. And if you could just update us on where that effort stands.
I exactly have the answer to you in my very last slide.
Okay, we can wait
I can quickly jump to the last slide to answer. Okay, if you can wait, then,
yes.
then yeah, it's really in the last slide. I have my answer to you.
That just increases the suspense. It's great.
Okay. Yeah, exactly. That's my strategy, actually. Yeah.
Sorry, I have a question about this slide.
Sure.
Is there an estimate for the fidelity of moving this electron, say, across like 10 sites?
So yeah, the fidelity, there are 2 fidelities here. One is the charge transport fidelity, because when you are moving the charge from left to right, actually there is a chance you will lose the charge. The charge will be released somewhere. For the charge transport fidelity, now we can achieve many 9, basically 99 point after the decimal. There I don't know 10 decimals after, so you can basically consider that we can deterministically transport a charge. And then another problem is about the spin transfer fidelity. So for the spin transfer, the transfer or the shuttling takes time, right? So definitely you are going to suffer from the T2 star, from the coherence time. So that's something you cannot avoid. Basically, if you want to avoid, you have to shuttle faster, and that's not a problem. But once you shuttle faster, you might start to expose your qubit into some faster oscillating charge noise because its environment is changing, right? You know, when you shuttling from left to right, it's not just you know, they are changing in time, but they are changing spatially. And so far, there have not been enough papers reporting this in silicon, but in gallium arsenide, what I can tell you is that if you shuttle it from left to right, the T2 star is pretty much the same as you just make it idle and wait at one side. So that's what I can tell you. And for silicon, we need to do more investigation because in silicon, the noise is actually, we say silicon is cleaner, but actually it's cleaner, but more complicated. Yeah. I'm not sure if it answers your question. All right, then I'll just continue. So yeah, we actually also, like I said before, we want to put some Cryo-CMOS chip, Cryo-CMOS control on the same chip to replace those bulky control electronics. This can actually help to reduce the latency, reduce the feedback time for error correction, etc. So we collaborated with Intel and we made this whole switch chip. You can see a fully functional chip is really only a quarter here. We made 4 copies of it. So it's only a 2x2 millimeter square chip, and we placed it at 3 Kelvin. It's not fully integrated as shown here, which is the eventual goal, but it's really a very important milestone that we show that we can actually put the, you know, just really shrink the size of all the control electronics down to a very, very little chip and put it into the fridge. It works at a low temperature. Our qubits were still at 10 decay because we were trying to test the performance of the chip. And we performed randomized benchmarking. And actually, I didn't show the error bar here. The error bar was about 0.03%. So actually, within the error bar, they are just the same fidelities. But still, if we want to finally integrate them all together, you know, they are at a different temperature now. We want to bring up the qubit temperature to also 1 to 4 Kelvin. So there have been very exciting works that I want to give credit to, you know, the work from Grenoble in the group of Tristan Munir, who was also a former postdoc in Levin's group. He showed high fidelity readouts can be performed up to 1 Kelvin. And in this two work at Delft and from UNSW, we show single and 2-qubit gates all functional above 1 Kelvin. And in the most recent work from Basel and IBM Zurich, it's very impressive. They show 98%, which is not bad actually, single qubit gate fidelity at 4.2 Kelvin. That is the liquid helium temperature. You can imagine how impressive it is, at least to experiment at least. All right, so now I'm gonna shift my focus a little bit to my work, and I spent a little bit too much time to talk about the background, but also I think we have different backgrounds, so it's worthwhile to talk about those. But now I'm gonna shift my focus to fidelity benchmarking of a 2-qubit unit cell. It's actually I would like to say that these two works are half of my PhD actually. So the first work I want to show is the 2-qubit character randomized benchmarking, which I did a few years ago. In 2018, our colleagues at Delft and Wisconsin Medicine, accurately Mark Erickson group, we together demonstrated a programmable 2-qubit processor in silicon germanium. So you can see we got all the T1, T2, and T2 ICO from this device. And don't judge on the numbers. These numbers aren't great. So, but I will show you the reason why they are not great. Actually, I have the answer here. It's in natural silicon. So I will come back to the isotope in silicon later. But still, I mean, we have all the characteristics. We want to. They are great, but still, we want to know the gate fidelities. So let me just quickly remind you again about the 2-qubit gate. In this particular device, when we operate the single qubit gate, the 2 electrons are isolated. And for this particular device, we turn on the 2-qubit gate by pulsing along the detuning axis, detuning the chemical potential. And you can see from the energy diagram, on the x-axis is a detuning. If it pulse from left to right adiabatically and come back to the left to turn off the exchange coupling. So we'll turn on when you increase the detuning, you increase the exchange, and you come back to switch it off. These 2 electrons, they are fermionic. So these 2 anti-parallel spin states will obtain extra phase. This gives you the condition of phase operation. So one step back, we firstly characterized all the single qubit gates. So here you see we did it in the convention using the conventional randomized benchmarking, and where you apply a sequence of random Clifford gates, and finally you apply a reverse gate, which just invert the net operation or the total operation of all the previous sequence. And ideally, if all your gates are error free, then you start from one state. The entire sequence should bring the qubit back to a one state, and you do the measurement, you get 100% return fidelity. But in reality, because of the error, and the error can accumulate, so when you increase the number of n, you will see an exponential decay. I guess most of you might be very familiar with it. So we perform individual single qubit randomized benchmarking on Q1 and Q2, and as well as simultaneously benchmarking both qubits. So again, don't judge on the numbers, but because it's a very old device, but we got around 99% single qubit gate fidelity, from the individual RB. And when we perform the simultaneous RB, we got the fidelities drop. So simultaneous RB are from, sorry, I didn't mention, simultaneous RB result are from the blue data points, and the individual RB are from the red data points. So the fidelities drop by 0.6 and around 2% for Q2. And we conclude this is due to crosstalk and leakage. Crosstalk is very easy to understand. I mean, you drive one qubit, you always touch the other one. And the leakage is actually a bit complicated. I'm not going into the detail, but you can imagine that, this is quite ironic, actually. We keep saying that a spin qubit, spin states it's naturally a two-level system. So you have only two energy levels. It's not like a transmon qubits. You don't have the higher harmonic harmonic levels. So there shouldn't be any leakage error, but in silicon, it's very complicated, because in the conductance band of silicon, you have this six-fold degenerate valley state. So they can give you extra leakage error. But again, it's in the old device, and for the valley states, for the valley leakage, we solve it in recently. So
on the previous, is it understood why there's such an asymmetry between the two qubits?
Thanks for the question. It's for multiple reasons. First of all, you can already tell that their coherence times are not quite the same. Qubit 1 generally has better coherence time than Qubit 2. So you can imagine for the let's say the depolarizing error or for Pauli errors, Qubit 1 is just relatively more robust against it than Qubit 2. And on the other hand, also we found it's this can also be affected by some local environment. We make it in silicon, and in silicon, the local noise environment can change from set to set, and maybe for some reason, Qubit 2 just suffers is exposed to more charge fluctuators, than Qubit 1. So these are the reasons I can tell you. Yeah.
I have a question too.
Yeah.
Sure. In the abstract that you sent out, you said that the single and two qubit gate fidelities are all above 99.5%, and that the average single qubit gate fidelities remain above 99% when including crosstalk and idling errors.
Yeah.
So I guess you'll get to that.
We'll get to that. That's the next work.
Okay, because these are all below 99.5%.
These are all below. Yeah, I'm going to that.
Okay.
Yeah, exactly. Yeah. All right, so if I continue a little bit, all right, so I think there's some misleading here. So now I'm just gonna rephrase I'll emphasize the outline again. So here I'm actually showing an experiment we did before the 99.5% work, and the 99.5% work is actually in this one, the one in the gray. I'm going to that one in a few minutes. So it's a little bit historic, and so later on, we perform two-qubit randomized. We want to perform two-qubit randomized benchmarking, and that ideally it's the same as single-qubit RB. You want to perform the two-qubit Clifford operations, and you want to interleave your two-qubit gate in the Clifford operations, and you compare these two results, so you can get the two-qubit gate fidelity. But actually, we perform the two-qubit RB. It's really an old device, and many things went wrong. So even the two-qubit RB wasn't working very well, so we applied the two-qubit RB, but we only obtained around 80% two-qubit Clifford fidelity, and isn't very great. But anyhow, this is actually because that yeah, we have this we kind of have this compilation overhead in the Clifford gate. You know, there are a lot of idle times, and yeah, so basically you can imagine that even this idle time here is comparable to our coherence time in the of the qubit. So we were actually not able to perform the two-qubit RB very well. And we took one step back. Actually, we wanted to perform so we were thinking that you know, the two-qubit RB wasn't going very well. So, but we were in a very well position for the simultaneous single-qubit RB. So why couldn't we just, you know, interleave our two-qubit gate by the simultaneous Clifford gate? And you know, that's a higher reference fidelity. Typically, it's actually also good. It typically gives you a better it typically gives you a tighter bound on the estimate of the target gate fidelity. But actually, it's not so trivial, because there's a issue here that your parallel Clifford gate does not depolarize your two-qubit error properly. So I'm gonna show you a little bit deep thought about the randomized benchmarking approach, actually. So yeah, so if you perform single-qubit RB, you know, you have a depolarizing channel, which is a single channel, which forms a uniform depolarizing error matrix. And you can fit a single exponential decay if you measure the return probability, and the P can basically give you the gate fidelity estimation. If you perform a two-qubit RB, it's actually the same story, except that now it's in a larger Hilbert space. So the Clifford operation is more complicated. But it's the same story. You just measure the joint return probability, and you can get a single exponential decay. And the P here again gives you the fidelity in the two-qubit space. So for the simultaneous RB, it went a little bit more complicated, because now you have three exponential channels, three noise channels, because it doesn't fully depolarize your error. It forms three separate channels. That's the channel of QB1, the channel of QB2, and the joint correlate or the channel for correlated errors. So actually, it turned out you will get P1, P2, and P12, the three depolarizing parameters in the different subspace. That's the subspace of QB1, the QB2, and the joint Pauli errors. So if you fit this one, actually, instead of one single exponential decay, but you will get a threefold exponential decays. Yeah. So this is very hard to fit. And I want to just go a little bit more here, that actually, you know, once you get the three numbers, the relation between the three numbers also tells you about the correlation and the correlation in the errors. You know, if P12 doesn't equal to P1 times P2, which is a general case, then you have correlated errors. But if P12 equals to P1 times P2, then basically you can disentangle the channels into, you know, two separate depolarizing channels, and that means you actually have no correlation errors, no correlated errors. Yeah, okay, so going a little bit more here, that so how we, like I said, it's very hard to fit the threefold exponential decay. So basically what we want to do is to just isolate them. So what we did here is, for example, if we want to isolate P1 from the other ones, ideally we want to find the sequence to keep P1 while keeping the other two to 0. So, you know, if you look at the P1 subspace, it's a depolarizing channel in QB1, but it's not very easy to isolate this one directly from the other one. What's easy to do is to isolate every single Pauli operator, Pauli channel, from all of the others. So what we did here is that we focus on sigma z, sigma 0 term. We want to isolate this one from all of the others. So this can be actually done very easily by, you know, we developed this method called character randomized benchmarking. So we actually applied two-qubit Pauli operator or Pauli gates at the beginning to the initial state row, and then we fit it into a depolarizing noise channel. So then if you sum up all the results weighted by the character function of the two-qubit Pauli operators in the representation of sigma z, sigma 0, then you'll be able to obtain such a noise channel. The method is very easy to do, but you can keep the P1 here while setting the other one to 0, and also setting the other two blocks entirely to 0. So you can actually isolate a single exponential decay from the others. And similarly, you can do it for the other P2 and P12. And the character functions are very easy to calculate, but we also wrote it down here. Well, but yeah, for experiment, basically we just add these two Pauli operators in front, and we we apply and then we apply simultaneous randomized benchmarking. We get the three exponential decay curves. If you three exponential channels. If you apply the four Pauli operators which don't involve any bit flip, then you get plus sign. So just to visualize it a bit better, you get plus sign in front of each channel. But now if you apply the Pauli operators with a bit flip on qubit 1 with no bit flip on qubit 2, you get minus sign on 2 of the channels, but plus sign on 1 channel. And similarly for the other 8 Pauli operators. So finally you can do some linear combination, do some magic, and you will be able to isolate the 3 channels. And similarly, you can do it for the interleaved randomized benchmarking. And we actually did that again from many years ago. We separated the 3 exponential curves for qubit 1 in blue, for qubit 2 in red, and for qubit and for correlated errors in green. So you can obtain the 3 depolarizing parameters. And don't be disappointed by the fidelity number, but this was really the state of art in a few years ago, that we got a 92% 2-qubit gate fidelity from H. And also we, based on the 3 depolarizing parameters, we actually estimate what's nice is that we actually had no correlated error between the 2 qubits, because within the error bar, P12 has no difference from P1 times P2. And this actually is because that we had very large qubit frequency difference, about 1.3 gigahertz, and also we had very small residual correlation between the 2 qubits, less than 100 kilohertz. All right, so that's really the state of art from a few years ago, and then I will show you the state of art right now, which is very high fidelity 2-qubit gate verified by GST. And before that, I would like to tell you that actually the choice of material has a huge impact on the coherence time. Many years ago, starting from like 2006, 2005, that's the earliest, that's the time when spin qubits just took off. We were all doing the experiment in gallium arsenide, because gallium arsenide has been shown to be very successful in transport measurement. But unfortunately, in gallium arsenide, you can imagine, gallium and arsenide, these two atoms, they don't have any zero nucleus spin isotopes. So you have zero nucleus spins everywhere, and due to this very strong hyperfine interaction, the coherence time is really short. So later on, we all moved to silicon, or let's say natural silicon, which contains about 5% 29 silicon, and 29 silicon carries a nucleus spin of 1, but still it's only 5%. So we can already see a 2 orders of magnitude improvement in coherence time. And later on, we since very recent years, we all moved to this isotopically purified silicon. We refer to silicon 28. Basically, we took out most of the silicon, the 29 silicon, but keep mostly 28 silicon, which has only 0 nucleus spin. And we actually can improve the coherence time by another 2 orders of magnitude. And you can see how big a difference it is. So consequentially, the material has an impact on fidelity, on gate fidelities. Let me focus on 2-qubit gate fidelity. In gallium arsenide, it was not even able to be benchmarked. You can only get a very, very brute quality factor. But in natural silicon, so here is the work I show you just now, that the state of art was 92%, and for single qubit gate it's above 99%, which was not, which was not the work I showed before, but from some other works. And in 28 silicon, actually, until 2 years ago, the single qubit gate already reaches 3.9, and 2-qubit gate reaches 98%. 98 sounds not far away from 99, but actually still quite a distance. All right, so now, again, this is a device. I'm just going to refresh your memory. This is a device that we use to demonstrate the high fidelity 2-qubit gate. Again, we have a coherence time very long now. It's 10 to 20 microsecond, average over 8 minutes. And yeah, conventionally, we do the detuning control, but here, from now, we symmetrically lower the tunnel barrier. It's the difference from the previous work. And actually, it's been shown in previous work that if you do it at the symmetry point, the coherence time can be improved by a factor of 5 to 6 compared to the detuning control. So I'm gonna skip how we found the symmetry point, considering the time limit. But for the CZ gate, but basically now we set them precisely at the symmetry point. So basically their chemical potentials are very well aligned. And now we perform the CZ gate. We want to make the CZ gate adiabatic. So basically, first of all, we need a complete characterization of the two-qubit interaction. We firstly characterize how the qubit frequency shifts as the function of the other, as a function of your pulse amplitude, as well as the function of the state of the other qubit. So you can see these two curves. They are from qubit 2, and the split here is caused by the coupling. It's coupling to qubit 1, and the other two here is the other way. It's the split of qubit 1 as a consequence of its coupling to qubit 2. And there's some background which can be naively understood as some stark shift. So we can extract the exchange interaction as a function of the barrier pulse amplitude, which goes exponentially. We fit it by a single exponential function, and we design a pulse shape looking like this. It's a little bit arbitrary shape, but if you put the shape into the exponential function, you can get a very nice cosine windowed exchange interaction. And we actually also measured the coherence time at different position, at different pulse amplitude. You can say when you pulse it deeper, actually, you know that you are going to kill the coherence. But when you come back to the idle, to the uncoupled regime, you have better coherence, which is actually kind of normal. But combining the pulse shape and the coherence time, we put it into a simulator, and actually we got really optimistic estimation. It's even above 3.9, close to 4.9. All right, so we start characterizing, we start benchmarking the fidelity. So this time, different from last work, which we use RB. Now we use GST, Gate Set Tomography. I will explain you the reason why GST is really good here. So we start by some manual calibration, using some conventional method, Ramsey or some bootstrap, such as OXY. We obtain the parameter set containing in total 11 parameters. You can imagine we have the frequencies of the two qubits, and we have the single qubit gate durations for each qubit. And each gate causes a phase shift on the neighbor qubit as well as on the same qubit. So we have in total 4 phase shifts caused by single qubit gate. And we fix the two qubit gate duration to be 100 nanoseconds. So we want to fine tune the amplitude of the two qubit gate. And finally, the two qubit gate induces phase shifts on each qubit. So there are 2 additional phase shifts to calibrate. We manually calibrate all of this. We feed it into GST. We analyze it. We obtain 98% controlled Z fidelity. And what's nice about GST is that you can actually see, you can isolate the coherent error from incoherent error. Again, coherent error means calibration error. That means your calibration didn't go very well. So here we can see that we actually have, it's an error budget of the two qubit gate. You can see we have huge IZ, ZI, and the ZZ error. That means our phase shift, the 2 phase shifts here, were not calibrated properly. The ZZ error means our CZ amplitude is not calibrated properly. But what's nice here, that's also why I became such a big fan of GST, is that you have this information now. That's the information that RB cannot give you, but GST can give you. So you can actually feed the information back to your parameter set. You can adjust your parameter, and then you can adjust it, about 2 loops. You really see the fidelity goes up. You really see that, you can see here, we adjust the pulse shape by only maybe 1 or 2 millivolts in the peak amplitude. Corresponding to the exchange interaction, it's only increased by 200 or 300 kilohertz. You can see ZI, IZ, and the ZZ error, they are greatly surprised, close to 0. And finally, we can reliably go across 99.5 CZ gate fidelity. So here I show you the real result. That's the core figure in this presentation. So that's on the right side. On the right hand you see the example 2-qubit GST sequence containing many single and 2-qubit gates, and we perform in total 1,685 such sequences in total. And combining all of the outcomes, we feed them into a self-consistent maximum likelihood estimator, and we can obtain the process matrix, or to be accurate, the Pauli transform matrix here, which gives us 99.65% fidelity with 0.15, the 2 sigma error bar. So GST also, in addition, like I said, GST tells you everything. So you can also get the error generator from it, which is the logarithm of the measured process multiplied by the ideal process. And yeah, the error budget I showed you before was obtained from here. So very nicely together with the other two work, I really want to highlight again that yeah, it was I say a hand result.
Yeah, thank you.
Yeah.
If you were to then use these calibrated gates and do randomized benchmarking, would you get fidelities that agree with the fidelities that you get from GST?
Yeah, it's a very good question. Actually, the thing is, we didn't come back to try the randomized benchmarking because we think that GST just works well, and yeah, we know that GST actually also handles non-Markovian error better than randomized benchmarking, and we suspect that we actually had some non-Markovian error in the sample. So we didn't come back to try randomized benchmarking. But what I can bring you a little bit more information here is that in the later work here by Mills et al., it's from Princeton, from Jason Peta's group, they actually tried both, and yeah, surprisingly, their fidelity numbers match really well. So yeah,
Okay,
that's what
yeah, just because like other groups use randomized benchmarking, like that's how IBM benchmarks their qubits. So if you want to compare apples to apples, then you probably want to also measure it using randomized benchmarking as for comparison.
Yeah, I think I agree with you partially, but not completely. I think that there are also, it also requires some thoughts, you know, requires some understanding in these two approaches and how they work. And yeah, so they actually, most of the assumptions made by GST and randomized benchmarking are actually the same. There are, they assume your errors to be Markovian. They assume that you have gate independent, I believe, gate dependent errors instead of gate independent. So mathematically, I think they should just give you the same outcome. And but I think in reality, in most scenarios, either I saw GST gives the same fidelity as RB. I saw some papers, you know, reporting fidelities using both methods, and either I saw GST reports the same fidelity as RB, or GST reports a lower fidelity than RB. So I've never seen anyone report a GST fidelity higher than RB. That's something I can share here. So yeah, that's also why we actually feel quite confident with the result. Yeah.
I have a very quick comment on your previous slide.
Please.
No, one before that. If you look at the lower left, at that URL you gave, you've reversed the I and the Y, so that www.pigsty.info takes you to a very different place than you were intending.
Excuse me?
You know, we're running out of time, so maybe we can move towards wrapping up.
Okay.
Paul was pointing out that you mistyped the URL, but I think most people would just Google pigsty, you know.
I see. Sorry.
It's that pickup, like.
The problem is most native English speakers would spell pigsty as he spelled it rather than as Sandia did.
Yeah. I actually, yeah, it's a very good point. I didn't even notice it before, actually. Yeah, it's very interesting. Pigsty, yeah. Okay, yeah. Now I got the point why they spell it as pigsty. Okay, that's the reason now. Okay, thanks for pointing out this little information. All right, so I'll just move forward. That's yeah, you know, I just want to show off the cover, but and later on, it's close to the end. That using GST, we actually also separated the fidelities. You know, the gate fidelity. Sorry, I separated the errors by you know, separate the coherent errors from the incoherent errors. Yeah, it's a better way to say it. So we actually see that we were still limited by the coherent error rate. Yeah, and I want to give some credit to the other work, and especially this work, the first work from the Andrea Morello group in USW Sydney. They actually took exactly the same approach, which is also the two-qubit GST, and yeah, they also show very high two-qubit gate fidelity. In the second one from Japan, they performed the two-qubit RB, and in the third one from Princeton, they actually did both to characterize the gate fidelity. So finally, I'll just quickly flash the results. So the fidelities and the process matrix and also all the error generators from all the other, not all the other, but some of the other gates. But I really want to highlight that even for the idle gates and for all the single qubit gates, we were really able to characterize them in the 2-qubit space. And actually, if you listen to the talk by people like Joe Emerson, he keeps saying that if you use RB, he's actually the founding father of randomized benchmarking. But now he started doubting that you use RB, you don't get the fidelity. You get the fidelity on the target qubit, but you don't know the error induced by RB on the other qubits. But here you can say that with GST, you can analyze it in arbitrary space you want, but no matter how many qubits you have, but okay, it takes longer time. The experiment will be more complicated, but it analyzes the error in a complete 2-qubit space. So you can really see the crosstalk very well. So I'll skip the error diagnosis here and firstly jump to the summary that, so in the first work I show you, we performed the character RB we also invented character RB and we performed it to distinguish non-uniform depolarizing channels. And we obtained the 2-qubit gate fidelity in natural silicon with the detuning control, if you still remember. In the later work, we use GST to fully characterize and optimize our single and 2-qubit gates. We obtain 99.65% 2-qubit gate fidelity in isotopically purified silicon with symmetric barrier control. And finally, I think I'll come back to the question before about what's the state of art and how many qubits can we offer to the users. So I actually intentionally want to advertise for my colleagues. We have this program called Quantum Inspire at QTech. And it's really qubits online. You can go to this website and really just go there, register an account. I think you will get an account a few days later. And if you contact me, I will talk to my colleague. You can get it right away. And now we have 2 spin qubits online since 2020, and 5 transmon qubits online also since 2020. Currently, the 2 spin qubits are temporarily offline because now my colleagues are doing a maintenance and an upgrade to a 6 qubit device. Basically, now we have a bunch of 6 qubit devices going for test, and a bunch of 4 qubit devices going for test, and we are gonna test them and pick up some of them to go into Quantum Inspire. And the goal for transmon qubits, I think, is to go for 17 transmon qubits. But I think that's I'm sorry, probably not 2022, maybe 23, maybe next year there will be 17 transmon qubits. But I hope this answers the very early question that if you intend to play with the spin qubits or transmon qubits from Delft, go to check out this website and register an account. And no matter what idea you came up with, what paper you publish, all the IP belongs to you, and QTech doesn't share any IP from you. So with all of this, I would like to thank you for your attention. If you have additional questions, I can answer them.
Questions?
Thank you.
Questions?
I have some more questions.
Sure. Yeah.
So it looked like some of your single qubit error rates were higher than your 2-qubit error rates. Is that right? So you see, I see infidelities higher than 1% here for some of these.
Indeed, actually, I by intention show you the worst single qubit gate here because actually our Y gates are significantly better for whatever reason. Our Y gates are so first of all, let me explain you the numbers here. First of all, the infidelity here, in the first row, actually here, the 0.3, 0.4%, they were analyzed in single qubit space, so not considering the crosstalk error on the other qubit. So right. The number in the first row, that's a number you are going to use to compare to the result from randomized benchmarking, because randomized benchmarking only tells you the fidelity in the single qubit space. And the second row is that when we drive only one single qubit, we don't touch the other qubit. So you can imagine the other qubit decohere while you are driving your target qubit. So there's decoherence error on the idling qubit. In addition, there's also unwanted crosstalk. You also mistakenly touch the other qubit. That's like a crosstalk or something. Oh yeah, similar things. That also gives you infidelity. So here you see really the infidelity in the 2-qubit space, they go higher. This is quite normal, I would say. And on the other hand, I didn't show you the Y fidelity here. For the Y gate fidelity, even in the 2-qubit space, we actually have them below 0.5%. the infidelity in the 2-qubit space. So there's some asymmetry between X gate and Y gate, which were not supposed to be there. I assume it's about it's related to some gate transformation, but anyhow, yeah, if you average over all of them, our single qubit gate fidelity has an average of 99.6 or 99.7% fidelity in the single qubit subspace, and have a 99.2% fidelity in the complete 2-qubit space. Our idling error has a pretty huge error, and it's because when I say idling, I really idle it for a very long time to let them decohere. So it's not a lot of people when they say idle, they actually do nothing, but that's not idling. Idling is you actually wait there, let them dephase. So that's why we actually have a quite huge idling error. But this error can be reduced if you just you say I don't let them wait there for hundreds of nanoseconds, but only wait there for 10 nanoseconds. Then they should be greatly surprised. But yeah, I hope this answers your question.
Yeah. So would you say then that the single qubit gates are actually noisier than the 2-qubit gate in this case, if you look at the effect on both qubits?
In this particular case, that's true. Actually, also in some other work, and yeah, if you listen to the talk by Matthew Reid from HRL laboratory, he actually keeps using my paper as an example to say that exchange interaction should be is better than microwave driving. So in HRL, they use exchange interaction to do single qubit gate as well. So they don't use microwave driving. So yeah, he used my work to as an example to say that. But I'm not fully convinced by that. I think in this work actually, because from the beginning, you can imagine. I mean, I was a PhD student before. I wanted to graduate, so I was just aiming at the 2-qubit gate. I didn't even bother to optimize single qubit gate. But actually, still to some extent, they were optimized. But yeah, it was not my focus. So yeah, I have to tell you that there is a huge space to optimize to further boost the single qubit gate fidelity. In the past, I performed the single qubit randomized benchmarking in exactly this device before this paper, and I obtained 99.9% from single qubit RB, but not from GST. So yeah.
Yeah. Now, if you were to scale this up to many qubits,
yeah,
would you expect the crosstalk errors to be like local so that you could characterize them using gate set tomography on like a local small set of qubits, or do you expect to get like long range crosstalk effects?
For long range crosstalk, yeah, this is also a very good point. So in silicon or in semiconductor, normally we assume that the errors come from charge fluctuators, which we refer to as charge noise, and from still some residual nuclear spin or residual hyperfine interaction, and which should also be local. Okay, charge fluctuator is not really local. It's still it has the impact across a certain range. So that cannot be considered as really local. But on the other hand, when you apply a microwave signal to a metal gate, the metal gate actually has a huge capacitance to a lot of qubits. So that can give you some non-local electric noise. So I agree that there will be local noise and non-local noise. It's a very good point that for non-local noise, I cannot imagine that we can estimate it properly using GST. For local noise, for sure, yes. But for non-local noise, I guess. So there was one thing that also I would like to flash here. That's also from Joe Emerson, that he was setting his cycle benchmarking approach, which always takes many qubits, all of the qubits as a altogether as a group to benchmark them. And yeah, so that can be something we can think about. But on the other hand, something just flashed into my thoughts is that maybe you can think about some experiment like you do GST on your targeted qubits, and if you want to check the crosstalk on the qubit far away from it, you can perform an idle GST on that qubit at the same time. Then maybe you can yeah, maybe in this way I think you can check the non-local crosstalk. But yeah, it's really just a brainstorm, and we haven't done any experiment like that. Well, if you have any idea, I mean, once our 4-qubit and 6-qubit device is online, go to perform the experiment. So.
Thank you.
Any other questions?
I would defer to the people in person if anybody has a question, but I have a follow-up on the final slide.
I don't think anybody has a question in person right now, except that we got to wrap up.
Okay, yeah, this will be likely fast. So I've been to the Quantum-Inspire site when you mentioned it, and it's very impressive, the difference between that and the commercial sites, that you don't have some 10-year forecast of achieving 1 million qubits, which all of them have, although of course that forecast has been time translationally invariant. What I'm curious about in your slide, since you have the short-term goals, but you gave a very intriguing description of the trade-offs between the spin qubits and the superconducting qubits. And this is purely aspirational. I know you haven't got on the record or anything like that, but if you were to show us a best case graph for the number of qubits you would expect as a function of time on the spin side and the transmon side. And I notice at your site, you're supporting both, so you're non-ecumenical in that regard. What would you hope for personally on the 10-year timeframe?
So can I
we can stop recording if necessary.
Paul, this is live on YouTube. The whole world is watching.
Yeah. So can I summarize your question as how many qubits would we have in 10 years or something like that?
Yeah, I mean, and comparing what you expect